definition is technically two rays that have a common endpoint form this thing called an angle. And if it opens in this direction, it's called positive. If it opens up in the other direction, it's considered negative. So what I want to do is I want to put it in a normal situation for us. We're going to put it in a coordinate axis, like this one. And what generally happens is the green one here, this is called the initial side. It's where we're going to start our angle. And it's always going to be along the positive x-axis. The initial side is never going to change. So if we're going to have a measure of 0 degrees, our initial side and the other one will be exactly the same. There's nothing in between these two. Once we start opening up the terminal side, that's the red one, we start getting this thing forming as an angle. And the further we open it up, the larger the angle is going to be. Now some common angles that we know are here. This would be a right angle, 90 degrees. This one over here would be a straight angle, which is 180 degrees. This one would be the larger one from where I started to where I ended. That's 270 degrees. And if I do a full circle and end up back where I started, that would be 360 degrees. So one full revolution of this angle, kind of like a clock hand, but backwards, counterclockwise, that'll give us 360 degrees. Alright, and if we go backwards, this would be a negative angle coming down here. This would be negative 90 degrees, negative 180 degrees, negative 270 degrees, and then back to the beginning, negative 360 degrees. And if you think about it, this can rotate around many times. So there would be 360. This would be 360 plus 90, 360 plus 180, 360 plus 270, 360 plus 360, better known as 720 degrees, which would be 2 revolutions of this angle. Alright, so if we're talking about an angle that's over here, let's say this angle measures 100 degrees. It's in the second quadrant. There is another way of measuring this. We can go the other direction and come up to it going in this direction. Well, to figure out what that's equal to, the sum of the blue and this orange line have to be 360. So this one has to be 260 degrees, but it's going to be negative because we went in its clockwise rotation. Remember, counterclockwise is positive, clockwise from the initial side is going to be negative. And these two measures are exactly the same, so we're going to call them coterminal. Two angles that end up at the same place. And all angles have infinite number of coterminal angles. For instance, I could take this 100 degrees, and why stop here? I can go all the way around and come back to it. So that would be a full rotation, 360 degrees, plus the original 100. So 460 degrees would be coterminal with 100 degrees. They're exactly the same angle. The measure on them is different, but where their position is after they're done is exactly the same. Next, I'd like to talk about what's called radian measure. So a radian, unlike a degree, has a very specific definition, and it's kind of a nice one. And we're going to define a radian to be the letter theta. So whenever you see theta in a formula, generally it's talking about a radian measure and not a degree measure. And we're going to let theta equal S over R. And I'm going to describe what S over R is. R, of course, is the radius of this circle. So from here to this point, from the center to this point out here, that would be the radius of the circle. S is considered arc length, and that's the length of this arc of the circle from the red line to the green line, just along the edge of the circle. That's the length of this circle. And if this measure is going to... So if I want a measure of 1 theta, then we need the S and the R to be exactly the same, so we're going to get R over R. And this picture over here, this is the true picture of what 1 radian measure looks like. This would be a picture of 2 radians. So here the length of S is going to be 2R. That's from here all the way back to here. And of course our radius here of the circle is just R, so we'd get theta is equal to 2R over R, and therefore this would be the measure of 2 radians. And then 3 radians would be right about here. Really, really close to a straight angle. Alright, so let's talk about this radian idea and coming up with some special ones. Here's a special measure of an angle. We know it's going to be 90 degrees. It's a right angle. Y-axis and x-axis running into each other. Some other things we might need to know for this. The circumference of a circle is 2 times pi times r. Depending, how you all around. This is only 1/4 of the entire circle. So we're going to change the formula into 1/4 of the circumference, which would be 2 pi r. Well, this is just the arc length now. The distance around a part of a circle is going to be pi r over 2. Alright, so if we go back to our other formula, we're going to have theta is equal to S, which is pi r over 2, divided by the radius of the circle, r. And if we simplify that, we're going to end up with theta is equal to pi over 2. So pi over 2 is the same thing as 90 degrees. If we double this, we're going to get pi is the same thing as 180 degrees. And if we double it again, we're going to get 2 pi is the same thing as 360 degrees. So this gives us a nice unit measure for transferring degrees into radians. We're going to use this one right here. It's the simplest of all of them. Pi is equal to 180 degrees. So if we want to convert degrees into radians, it's kind of simple. Say we have 100 degrees, and I want to change it into radians. Well, I'm going to do it by unit conversions. And what we're going to do is we're going to want to get rid of degrees, and we want to change it into radians. So there are pi radians for every 180 degrees. So when we do this, the degrees are going to cancel. You're going to get 100 over 180, which is the same thing as 10 over 18, which is the same thing as 5 over 9. So our final answer is going to be 5 pi over 9 radians, and that'll be the same thing as 100 degrees. This also works backwards. If we want to start with something like 2 pi over 3 radians, there's a reason I'm not writing rads, but we'll come back to that later. We're going to multiply this by a unit fraction, where we get rid of the radians and we introduce degrees. So I'm going to put the radians in the bottom, since this is technically RAD here. And that means there's going to be pi radians in the bottom, and we're going to convert it to degrees, so we'll put 180 degrees in the top. And after a little bit of simplification, the pi's are going to cancel. 3 goes into 180 60 times, and we're going to get 2 times 60, which is 120 degrees. So 120 degrees is the same thing as 2 pi over 3 radians. Now the reason I'm not putting RAD after this is that when we do this formula, theta equals S over R, S is measured in centimeters, and so is R. So when we do this division, the centimeters are disappearing, and this whole idea becomes unitless. Radians are a unitless measure. That's the reason we don't need to write it here. The only time you really need to write it is if we're, change our radians into decimals, and it gets kind of confusing just writing 1.2. You can write RAD next to it, but there is no reason to write it other than to recognize what